Pardon. And Elliott's been working very closely with the Large Hadron Collider over on the border of Switzerland and France. All right. And it's one of the largest science projects on Earth right now. And Elliott's going to fill us in on the goings-on, the recent updates, and progress of the collider. It should be a very interesting presentation. I just wanted to mention, I saw Elliott's presentation about this time last year over at Centennial Hall, and he had packed the place. It's a very, very interesting presentation. I hope everybody enjoys it. Elliott?
Thank you. Thank you very much. So, thank you for having me over here. What I'm going to try to do is give you a flavor of the kinds of things that we can do with this thing and why we built it. You may not be able to see it. This is a picture from the inside of one of these massive detectors at the Large Hadron Collider. And what you can see here is a person actually standing. I don't know if you can all see it, but there's a person standing here in the middle of this detector. This is actually during the construction period, and this object is going to eventually get pulled all the way to the front of it. So it's going to cover the whole space. So to give you an idea, this is the border between France and Switzerland. What you can see up here is you're looking you can see some of the Alps in the background, and I'll just point to it. This is the Geneva airport. So it gives you a size and a scale. The red circle here is where the accelerator exists. So the accelerator is about, 27 or so kilometers in circumference. It's a very big device, and each of the what we call detectors sit at some of these intersection points, and that's what I'll be spending some time talking about. This is one of the components. This is actually a magnet that is being installed, and it was actually brought from one side of the site to the other on this very interesting truck. This truck is, I don't know, something like 30 independently actuated wheels to keep the thing level and so the thing can move. And this thing weighs tens of tons, this magnet. It's actually going over this site, and eventually it gets dropped down underneath the ground where it's going to sit for, it's about 300 feet underground. This shows you actually in some of the installations, you can see some people here working on it. And again, this is just to give you an idea of just the size of these type of experiments. So what I want to do is give you a little idea of why we actually built this thing. And so I'm going to kind of give you a primer on particle physics. So this thing, the Large Hadron Collider, is meant to, or built to actually study something we call particle physics. And the big questions that one can ask are, what are we made of? What things are actually, people have always been studying for a long time. What are the most fundamental things that make us up? And you can go back all the way to the Greeks, where they talked about the 4 basic elements, down to things like atoms, and we now know there are neutrons and particles and smaller than that. And so that's kind of one of the big basic questions. What are the most basic particles? And then something that may not be so obvious to you, but there are interactions between the particles which actually give rise to all the kinds of things that we know about today. So light, gravity, these are the forces that actually interact between particles, and they actually have big implications for how things work. A big question which you might have heard of is something, what is the origin of mass? Why do things have mass? Why do things interact with gravity? And one of the things that can be actually hopefully answered by this big machine is what is the origin of that? And finally, what I'm going to talk about today is what is dark matter. You might have heard this in the nomenclature. People talk about dark matter and dark energy. And what we hope is actually that this machine that we're building will actually answer some of that question, tell you exactly what that is. So let me start off by the 4 forces. When we go back to particle physics, we can actually describe all the things that are what we call forces in terms of 4 fundamental forces. And the forces that we talk about are gravity, the electromagnetic force, the strong and the weak. And they can be described relatively easily here. Gravity is probably one that you're most familiar with, and that's just basically what keeps this planet on the ground. Why do things fall down towards the center of the Earth? It's because there's this force called gravity. The electromagnetic force is probably very interesting to you guys because both the transmission of ham radio occurs through electromagnetic waves, but actually an electromagnetic wave also is the reason that you don't fall through the floor, because the repulsion between the basically the particles in your feet and the floor, is an electromagnetic force. Then there are two forces that you don't really hear about too much, but those are the strong force, and that's what keeps the protons and neutrons and nuclei together. And then the weak force is the force that's actually responsible for why the sun shines. Without that, we wouldn't know it. Actually, people 100 years ago thought that the sun was powered by gravity, and then when you work out the numbers, you find out that the sun would only have been shining for about 100 million years. We believe the sun's been around for billions of years. So the other thing that we can discover with this big machine is actually trying to understand the structure of matter. And the way we now understand it is originally people thought about things called atoms. Then there were the nuclei, which is smaller still than the atoms. Nucleons are things like protons and neutrons, which are these dots here that you can see inside the nucleus. And now we believe that there are things called quarks, which the nucleons are made up of, and we're possibly even probing beyond that. Maybe there are things that are smaller than that. And the reason that we have to build these such large devices is in order to get down to and see things this small, we actually have to have things that are very, very energetic. And I'll talk about that in a second. So, ordinary matter that we know of is made up of, in general, 6 quarks. They have these very strange names, and I won't go through them, and 6 leptons. The leptons, probably you've heard about things like the electron. Well, there are actually 6 of them. Some of them are called neutrinos, and some of them are called electrons and muons. But that's what we believe is making up all of matter as we know it. And when I talk about matter as we know it, that is what we call ordinary matter. All these pieces that we have are part of what we call the standard model of particle physics. The standard model is basically that. It's just a model. It's a way of writing down our understanding of how all particles fit together. People have said, though, that it's so precise. There have actually been measurements within the standard model that are precise enough that are the same precision that if you were to measure the distance between, say, Los Angeles and New York, you would actually be able to measure the distance down to the width of a hair. And that's the same precision that we actually understand things in this thing we call the standard model. Okay, let me talk about dark matter. Dark matter is a really interesting thing. It turns out that we believe that if you look out in the universe, there's this stuff that we call stars. We know about that. Well, it turns out that there are also evidence for other things that we know cause light to bend. And it turns out that gravity can bend light. And if you look out in the distance, this is called a bullet galaxy. What happened is actually that 2 galaxies collided together. The red stuff is the ordinary matter, because it can interact with more than can interact through gravity. It actually tends to clump together in the middle. But the stuff in the purple is actually the dark matter. The dark matter interacts very, very weakly with itself, so it kind of flies by as these 2 galaxies collide, and yet the stuff in the middle is left. So this is one of the pieces of evidence of dark matter. Here's another example of dark matter. You can see that here and here, these are actually galaxies. And you can see with this, and what you can see is that they actually look bent. They look like arcs instead of little ovals or circles. And that's because between us and the galaxy, there's actually this dark matter, which is bending the light. And that's called lensing. And there are many, many examples of this out in the universe. Here's an example of what we would see if you had some galaxy out towards the left here, and you're sitting out here and looking at the sky. There's this thing, which are these patches that are supposed to be dark matter. And between us and that far distant galaxy, there's all this dark matter, which we now are looking to map out. And the question is, when we look at that, can we tell that there's actually stuff there? And it turns out that there's lots of evidence for that. And in fact, if you were to count up all the matter in the universe, the stuff that we call stars and gas and all that, that's this part right here. So it turns out it's only about 5% of the known universe is made up of what we call ordinary matter. And when I say ordinary matter, those are the things like the electrons and quarks and all that stuff. The rest of it, well, there's this 25%, which is, or 23%, which is the dark matter. And the remaining stuff is something called dark energy. And I'm not even going to talk about that. But that's even less well known. People don't even have no idea what that is. So why am I talking about this? It turns out that in our current understanding of the world, that we believe that the dark matter is another fundamental particle. So I've been talking about these things like quarks, leptons, and all that stuff. Well, dark matter, we believe, is yet another particle which has not been seen. And it turns out that a lot of the theories that exist, this dark matter is part of a new theory, which we think we can actually see and prove at this Large Hadron Collider. So my point is that the Large Hadron Collider may actually produce this dark matter, and we'll actually see it. And by doing that, we'll actually have a lot of evidence for what actually occupies another 25% of the universe. Okay, so the point of particle physics is to actually look for all these particles, and hopefully what we'll see is that they will produce these very, very striking signatures inside of the detectors. Okay, so that's the end of my little, let me tell you one more thing. So this equation you've probably seen before, right? And if you haven't, I'll tell you what it is. The E over here just means energy. The C squared is you take the speed of light, you multiply it by itself, that's C squared, and M is the mass. So if I want to produce a particle of some known mass, I have to have an energy that's multiplied by the speed of light twice, or squared. And if you know the speed of light is this number here, it's a very, very big number. What that tells you is that even to produce a very small massive particle, you have to have a lot of energy. And what that tells you is that you have to build very, very big experiments. Okay, so that's the end of that little primer. So now you know all you need to know about particle physics, and probably all I know about particle physics. So in order to get to those energies, people have been building colliders for a very, very long time. This is a picture of J.J. Thomson, who was the person who discovered the electron. And he's got this little tube here, which is effectively like a vacuum tube. So I'm sure you guys know all about those. It's effectively a vacuum tube, and he was able to produce little streams of electrons and see them. I think it was in the 40s and 50s, people started building these things called cyclotrons. And this is the first one. There's not a good scale, but this thing is about the size of a silver dollar. So, this scale. In the 70s, we built even bigger accelerators. This is that Stanford Linear Accelerator. And to give you an idea of the size of this, I worked there when I was an undergraduate. This is a car down here. So it's a pretty big device, but it's not the biggest. In the 80s, if you ever go to Chicago, just outside Chicago in Batavia, there's an accelerator called Fermilab. This thing, I believe, if I remember, is about 3 miles in circumference. So if you want to see the size of a car, this is a parking lot down here. It gives you an idea. And now we're at the LHC. And the LHC, as I said before, this is the Geneva airport. This thing crosses the border. Well, actually, you can see it. This is the border between France and Switzerland. You can see, believe it or not, that it actually crosses the border many times, and that's just because, well, it's those French and Swiss. They couldn't. The border is not straight, so it crosses it many times. Okay, so this will give you kind of an idea of how long it's taking to come to fruition. The actual design of this was started in the mid '80s. And it's continued, and it was only completed in 2008. So it's a project that's been moving on, on a scale of decades. This was actually when they first proposed one of the detectors of the experiments was in the early 90s. As the University of Arizona joined this in 1994, the experiment, even though we had joined it and been proposed, wasn't officially approved until after we joined it. That wasn't because of us; it just happened to be the time scale. And then this is, in 2007 was when they actually had the last magnet installed and the whole construction was complete. This is actually one of these magnets. This is a superconducting magnet, so it's filled with liquid helium. And I don't remember the length, but it's something on the order of 8 or 10 meters long. It's a very long device, but if you think of how long this thing is, it's 23 kilometers in circumference. You got thousands of objects. And then the experiment was completed. Let me give you an idea of what happens in this accelerator. So in Atlas, what happens is that there are 2 tubes, they're called beam tubes, and we're going to inject 2 beams of protons. So those are just like hydrogen, the nuclei from a hydrogen atom. One goes this way, and the other goes this way. The reason it goes in a circle is twofold. One is that in order to, these beams, if you have 2 beams of particles, you want them to collide. The number of times that you actually have something happen when the beams go past each other is small, so they recirculate the beams many, many times to get them to get collisions. In order to go in a circle, remember your high school physics that a charged particle going through a magnetic field bends. And so there are these large number of magnets like we saw before, and by having these magnets, it causes them to bend. One of the problems of a particle that bends is it loses energy. And so there are these, what are called accelerator cavities, or RF cavities, which pump energy back into the beam to make sure the beam continues along its path. And then there are regions where the two beam pipes are brought together and the beams are allowed to collide, and that's called a detector. And so the collider, the big part of it, is meant to just allow particles to go around in circles and hit each other. But then you want to find out what happened, and that's done in these detectors. So I'll show you a couple of pictures. This is, again, one of these magnets that's being installed. This is one of these big RF cavities. And so you have RF energy that's pumped into the beam, and basically the particles ride along it like they kind of surf along this RF wave. This shows you, it's a little bit of a movie, and it basically shows, as we zoom down into the underground cavern, remember this is about 100 meters underground, it's going to open up to show you what it looks like. And this is one of the detectors that sits inside this cavern. You can kind of see, it's made up, it's like an onion. There are various layers that compose it. And this is showing you what a person would look like as they walk along. It's going to zoom out, and you'll again kind of see what the scale of this object is. The person is right there. And here's the schematic. I'll talk about it in a second. Again, it's kind of got an onion-like structure. And the reason for that is we're going to have these two beams collide, and we're going to have stuff coming out of it. And we want to be able to identify what that stuff is to then infer what took place at the collision point. And that's the goal of this. So here's actually what happens. This is a little movie of different types of particles going through a cross-section. So there's the beam pipe. This is an electron. And what happens, you can see that an electron comes through here, bends a little bit, and then splashes in here. This is a photon, and a photon doesn't leave any signature in here, but it splashes in here. A proton goes in the opposite direction of the electron because there's a different charge. It moves in this direction, splashes in the second part, and a neutron splashes, but it doesn't leave anything in here. And finally, this thing called a muon here goes up and reaches all the way to the outside. So I'm not going to go through all the details of it, but what that basically says is that if you have different types of particles, they interact differently in the detector. So by looking at the interaction detector, you can then infer what type of particle that was. And by knowing those particles, you can infer what took place in the interaction. So that's what the detector does. The reason it's so big, this thing has the length of it is about 150 feet. So it's about half the length of a football field long, and then about something like 75 or 80 feet tall. And the reason it has to be that big is because since the particles, the protons that are colliding have such large energies, it produces secondary particles which also have large energies. So to collect those particles, you need a very, very big thing. And this thing is called a detector. This will give you some of the numbers. So it's 46 meters long. It's about half the length of a football field, and it weighs about 7,700 tons. If you were to give you a scale, in terms of 747, so if you took 100 empty ones, that's about how much this detector would weigh. We're going to actually write about 32 terabytes of data. Again, a big disk that you can go buy at Best Buy now can hold about a terabyte, and we're going to write about 1,000 of them a year. So it's a very, very large amount of data. This will kind of give you an idea of the energy at the center when the two particles hit. If you were to translate that into energy, it would be 100,000 times hotter than the sun. We'll have lots of collisions. And the other thing that's kind of interesting, shown in this picture, is that in order to build these large experiments and do something with it, you need a lot of people. So there are about 2,500 physicists, so people with like a PhD who are working on this experiment just in one experiment. So this gives you some of the things that we did here at the University of Arizona. One of the things that we did was we helped build what are called calorimeters. And calorimeter just means something that measures energy. And as you saw in that little movie, when these particles splash in the detector, they deposit their energy. And so we were involved in building that. What's interesting about it is that our group here at the University of Arizona is considered a small group in particle physics. We have 5 faculty members. And we originally were associated with the experiment where the collider called the SSC down in Texas, which was canceled about almost 20 years ago now. At that time, we went and joined this experiment, and they had a very different design for their detector. And this will give you an idea. The detector that they were building, which is called these calorimeters, are right here. And when we joined the experiment, we convinced them that that design was the wrong design. And so what happened is that the design now looks like this based on the contributions from the University of Arizona. We actually were able to convince them that they want to put that thing, if I go back, this thing, inside the detector, and now here it is, and it's actually located here. So by doing that, it changed drastically the configuration of the experiment, and we believe it actually will make the detector more robust, that it won't have as much background in it from other signals. So this is actually the construction of it. Is one of our technicians working on it. Here's this detector. So the detector is really not that big. You can see that it went from being something that's the size of, as tall as this room, to something that you can sit on one of these tables. And by doing that, so this is one of the ones that we built. You can see it being crated up to go off to CERN. So it was built here in the basement of the physics building, and then it had to be shipped all around the world. What's great about it is that, it had to go on, it was kind of like trains, planes, and automobiles. It went on a truck. You can see it here being lifted onto the truck. Then it went on to a boat, and then it was on the truck again. And it went all the way to Switzerland, and then they dropped it. right when they got there was a crane operator there. He picked it up, and he didn't have it on his crane, and it fell right off the crane. And this is just some of the pictures. This little circle here was supposed to be in the center. It's one of these, I don't know what you call them, but these, it's supposed to show you that the thing hasn't been shaken. Well, you can see it's been shaken. Well, they went through and looked at it. It turned out it was built robustly enough that after a few months of refurbishing it, they were actually able to install it. You can see it actually being installed here. So it actually. One of the things, as I said before, is that the data that's produced is a very, very high level of data. And one of the things that's actually come out of that is that people have had to look at new ways to handle large amount of data. And that's created something called grid computing. And the particle physics community is actually driving this whole thing because of the amounts of data. This is actually one of the grid centers, and each of these is a multi-CPU processor. You see, we have buildings with rooms of these things located all around the world. So the data gets shipped to these sites all around the world. It gets processed, and eventually the results end up on your desktop. But that's what the process is. Okay, so a number of years ago, somebody said did a survey saying, well, what are you going to see when you do this? Because it's very, it seems very, you have these hypothetical things that you're looking for. Is it really real? So they did a survey, and it turns out that nobody really knows what's going to happen. We're going to turn it on and hope for the best. So this is just a recent cartoon that somebody did. So in September, about a year ago, it was really exciting. I actually stayed up to see this. They actually turned it on. And they were able to, within an hour, send protons all the way around the ring, which was actually very good because the previous time that they had turned on a machine this size, it took them a few days to a week to get that to work. So within an hour, things were working great. This is a movie of this is, again, the Atlas detector with stuff that actually hit it from this first time that they turned it on. And you can see, they did, it's kind of a cheat. They actually took the beam and hit it into a piece of metal upstream of the detector, and you get this splash of stuff coming down. But it makes a very dramatic picture. But then, 9 days later, we had this accident. And the accident was much more severe. When I first heard about it, I thought, it's a little thing. This is the junction between two of the magnets. And you can see this thing actually is completely shifted. To give you an idea, remember these magnets weigh tons. And you can see this is actually the floor underneath the magnet, and this is the mount, and it broke the concrete, completely destroyed it. And it turns out that the culprit was, these magnets are superconducting, and this gives you a picture of the conductor that connects two magnets. And it appears that what happened was that the junction is made by, there's copper here, the actual superconducting material is here, and then there's solder. Basically, it's kind of solder. You put this whole thing together, and this is what it looks like. So here's the copper, there's the superconducting conductor here, and then there's supposed to be solder, and it appears that somehow they didn't put enough solder or any solder at all. And that created a resistive junction. And when you're putting that many amps, it turns out that you get massive burning. I mean they had megawatts of power going through this thing where it became where it was no longer superconducting. This is the burning that you can see. Here's again some of the burning that actually occurred, and give you some of the numbers. There are all kinds of things that happen. I mean, I'm sure many of you know that anytime you have an accident of this scale, it's a series of things that happen, not just one. So in addition to the lack of solder, there was a detection system that was built in the magnets but not in the junctions. And then that protection system in the junctions, which they did have, was set about a factor of 3 or 4 too high. So it couldn't actually have seen the failure until well after it happened. So they had about 4 megawatts of power going through that system, and it was enough that they blew open a hole in the helium enclosure. But when you do that, something that's liquid helium, which suddenly becomes room temperature, it's explosive. And you had explosive expansion of the helium, and it completely blew the magnet off. It actually blew soot down the beam pipe about 700 meters in both directions. Here's another picture, and this just shows some of the soot as it was being forced out of some of the ports in the magnet. There's an overprotection system, but it wasn't big enough to handle this. So it turns out that they had to remove 53 magnets. Now, it doesn't sound like a lot, but remember these magnets are 300 feet underground. They're all around the ring, and they have to be ported to a few access ports and brought all the way up to the surface. And they were also at cold liquid helium temperatures. So there's soot that had to be retrofitted. It turned out it took them about a year to do that. Here is the facility where they were actually testing and retrofitting the magnets. This gives you again the scale of magnets. So here's a person, and there's one of the magnets in the process of being retrofitted. And here's one of the magnets after they had finished. So they were able to repair it, and we actually, on November 23rd, they were actually able to have their first collision. So even after they started up, they only started putting beams in one direction. They actually had their first collisions just about 2 months ago now. And this is actually, I guess I forgot to turn on the sound, but this is the day that they actually had their first collisions. You can see people in the control room. And this is the very first event that they had where they actually had 2 colliding beams, and this was again on November 23rd. So this is 2 months ago. Okay, so then the milestones are such that we turned it on the first time about a year ago. There was this accident 10 days later. It was restarted just a couple months ago. We had our first collisions, and then they ran until December 18th. So it was actually about a month of running with these first collisions at very, very low energies. But in spite of that, at the time, by the time they had, a week after they had actually had first collisions, it had become the most powerful machine on Earth. It had overtaken the Fermilab Accelerator outside of Chicago. So what's going to happen next? Actually, in less than a week, they're going to turn on again. So they shut down after they had this engineering run, and they're going to start taking data for at least a year. It's actually probably going to be closer to 2 years. At that point, they'll become a discovery machine. So we should actually have an opportunity to see some of the things. And hopefully this year, we'll actually start to see the first results from the machine. Maybe we'll even see hits of dark matter. So this is just a brief thing. You know, one of the things that people always ask, well, why do you do this, and does it have any impact on what we do? And the answer is yes, in kind of an ancillary way. It turns out that some of the more recent cancer tools are proton accelerators, and these are direct spin-offs of types of things that we've seen. In fact, there is a cancer center using this technology at Fermilab, just outside Chicago. The other thing which you may or may not know, you may have heard this, is that the World Wide Web actually was developed at CERN as a way for the scientists to communicate with each other. And of course, now it's taken on a life of its own. The scientists don't own it. They basically developed the language, HTML, and that's now become pretty much a standard, which has since completely overtaken the particle physics community by far. But I do remember as about in the early 90s of being introduced to this language, saying, oh, what's anybody going to do with this? I mean, it's kind of cute, but we were using it, to share documents. Now it's doing much more than that. And this I kind of like. This is an article from I think it was the New York Times when Edison invited a reporter down to his lab in New Jersey to talk about the light bulb. He had just developed the light bulb, and he brought somebody down, and the reporter basically said, it's not clear what this thing is going to do. Why would anybody want these light bulbs at this great gas light system? And that's how we kind of take it for the LHC. And we're developing these tools to understand basic science, but who knows? There's a lot of things that come out of it. Some of them direct, more of them secondary, but maybe even just by discovering these new particles, just like the discovery of the electron, could lead to new interesting things. This is just a picture of some of the people. We have 5 faculty, a number of staff currently on our program. And one thing that we're really proud of is the fact that we've always involved undergraduates at the university, and actually a number of them have been over to Geneva to work on this experiment. So that's it. I just wanted to end with this. It's kind of an interesting picture. It's just the scale of it is always impressive to me, and I'll just end there. Thank you for your time. Yeah.
The God particle, or is it the Higgs boson?
That's right. So the question is the Higgs boson.
Is that the only particle that they're expecting to isolate or to actually discover? Or?
No, actually, so the question was whether or not you could, there's something called the Higgs particle, which I didn't really talk about. Is that the only particle that we expect to see with this machine? And actually, no. The answer is there's a whole plethora of things that we hope to see. One of them is this dark matter particle, which could be a supersymmetric particle. And the Higgs particle is another particle, and that's the one we believe is responsible for why things have mass. If supersymmetry exists, this dark matter candidate, then we would actually see a whole plethora of new types of particles. Yeah.
Is any of this data that the collider collects going to be offered up through the Planck system?
Through the
Point system.
I don't believe so. So the question was, is any of the data going to be offered up through the point system?
Point, the Berkeley open off infrastructure for network.
Yeah, so no. Typically what happens, there are very different scientific communities. So the astronomy community, for instance, is very much into open data, where they'll share all the data, they'll show you where all the stars are. The particle physics community isn't necessarily a closed community, but often there are a couple interesting aspects of particle physics. One is just the size of the data. We're going to have petabytes of data before we're done. And then the other thing, which is more kind of a cultural thing, is that in order to analyze the data, there's a very, very detailed process of doing that, including all this software which has been developed to actually read back the data. And it requires a huge amount of overhead. In fact, I still don't even understand it, the software. So it's mostly because of cultural reasons that's really not offered up for people to look at themselves. But there's no real underlying reason why we don't. It's just that culturally we've never really done it.
Well, not so much as to look at the data, but to process the data in a grid computing atmosphere.
Then I guess I don't understand your question. I mean,
is any of the data that is collected going to be offered up through the grid computing network around the world, so that computers like the ones I have at home can chew up some of this data?
Yeah, no, the grids that people are using are actually basically systems that are either at national labs or big university systems. So, and there's no particularly, well, the reason is because, again, it's running very, not proprietary, but our own version of software. And so each of the systems has to have that software system installed. And that system has a very, very large database and a very, very large software turns out has a lot of overhead to actually install. You can't just take a package and tar it and install it. Turns out there's a lot of stuff that goes on behind the scenes that has to work. It's because we're particularly bad at managing software that it happens that way. It's not because we want people to not have access to the data. But so yeah, it's not something that will be running in the background like the SETI type things that happen. It's something that actually has to have a dedicated machine that loads all the software and all the data, crunches on it, and then spits back the answer. So they're part of these very, very large data centers that are being installed. And these centers have 1,000 CPUs, and that's where the data will be processed.
Okay, thank you.
Yeah.
I got a question about the helium. Helium at one time was considered a strategic source, or strategic, what do you call it?
Resource?
Resource, yeah. At multiple kilometers wide, how is this thing going to guarantee its helium source?
So that's a good question. So the question is, we use a lot of helium, and how are we going to guarantee it? There are two things. First of all, helium is mined, which you may probably know. So you can't just collect it from the atmosphere or something. So you're right. There's a limited supply of helium out there. In fact, one of the delays in getting the thing started was actually getting enough helium because there was so much helium in the system. The helium actually is recirculated. So the actual usage of helium, and I don't know what the exact number is relatively low as long as they don't have an accident like they did. When they have an accident like they did, they lose a lot of helium in the atmosphere. But once they have purchased the helium for the system, it's a closed loop system, and it's recirculated, it's liquefied. And so forth. So they have a big helium liquefaction plant on site.
I have seen some drawings that depict the
I'm sorry.
true circle, and some that depict it as an ellipse. Which is it?
I'm sorry, I didn't quite hear.
Some drawings show it as a circle, true circle, and some drawings show it as a possible ellipse.
Oh, you mean the collider? Whether the collider is it's a circle.
True circle.
It's a first product. Yeah, I mean, obviously it's going to have some defect, but it's basically a circle.
And then some other drawings show it as a tilt.
Yeah.
It's a tilt, 400-foot tilt. So my question is, if it's tilted, the question is why?
Oh, the tilt, and I can't remember how much of a tilt it is. I believe that's correct, that there is a tilt. The problem is that if you look at where it goes, the thing actually goes underneath the Jura Mountains. The collider goes across the border between France and Switzerland, but also goes over the mountains. And at some point, if you get too below the mountains, you actually start hitting water and things like that. So I'm not positive, but I believe that the reason that it has some sort of inclination is basically because of that. But I'm not actually positive about that. Yeah.
Is there any reason why you use liquid helium instead of liquid nitrogen?
Yeah, so the question was, why do we use liquid helium versus liquid nitrogen? To get to the superconductor at a certain temperature. And it turns out that there are very few superconductors that superconduct at liquid nitrogen temperatures. So to get down to the superconductor, it's kept about 2 degrees, 1.9 degrees Kelvin, which is right above absolute zero. So I believe the superconductor is niobium, and that one only superconducts at very, very low temperatures. Liquid nitrogen wouldn't get low enough for temperature. Yeah.
Presume running this machine takes a great deal of electricity. Presume a significant fraction of at least the local electric supply. What kind of procedures have to be developed and how much it does use?
Yeah, that's a good question. I don't actually know. The question was, how is this connected to the grid, the electrical grid there? There are, it's certainly, let me answer that in kind of a backwards way, in that one of the issues has traditionally been that they've shut down both during Christmas just because of the holidays, and also during the summers because summers typically have a large energy draw. So there is an issue in terms of power, and I believe, I don't remember what the actual number is, but it's basically enough power to power a small town or city in Europe. So, well, small town anyway. So it is significant. And one of the reasons it uses superconducting magnets is actually to reduce the electrical draw, because otherwise it would be impossible given the infrastructure to actually run it.
How do the detectors discern from events happening outside the ring, so to speak?
So that's a very good question. You know, even at 100 meters, so the question is, how do you discern that basically the events are happening from the collisions as opposed to something else, right? And it turns out because it's so big, it's actually bombarded by cosmic rays all the time. So we actually see a large flux of cosmic rays, and when there was no beam, those cosmic rays were actually used to help see whether the detector was working. So we could actually see cosmic rays coming into the detector, and there are lots of pictures of things like that. The first way that you know that it's actually happening from the beam is we know when the two beams are going to hit each other. And so the events are usually timed such that we only open up our gates and trigger the events during collision times. So that reduces, some of the rate from cosmic rays. The other thing is that cosmic rays in general, those events don't point back to where the collisions happen. And most of the events from our detectors will. But there are times when we'll have a real event which overlaps with a real cosmic ray. And in those cases, we have to use other tricks, which are just kind of tricks of software analysis to get rid of those things from them. But yeah, there actually are a problem. Yeah.
When you feed the circle panel with whatever particles that you send in, do you send a steady stream of these, or do you break it down to like one or two?
No, that's a great question. So the question was, what are we sending through? So first of all, we're sending protons. So how do you make protons? Well, basically what you do is take a bunch of helium gas, hydrogen gas, and strip off the electrons, and that's easy to do, and then you have protons. So you send protons one way and protons the other way, and they're sent in bunches, and I don't remember the exact numbers, but there are bunches of protons, and there'll be hundreds of bunches located throughout the ring going in one direction, and hundreds of bunches going the other way, and these bunches will be timed so they collide at these interaction points every few nanoseconds, actually. So the rate of them is actually going to be very high.
In that regard, how do you control so that the collision will actually happen inside one of the detectors?
So in order to make sure that the two bunches collide inside the detectors, the bunches are kept going around by these RF cavities, these RF generators. And those RF generators have a well-defined timing structure. And so that timing structure, and I forget what the range is timed so that a bunch is basically being pushed along one of the crests of these RF waves. And so by the fact that you have some going this way and some this way, you could actually time them in very easily to make sure they collide at the right points. The other thing which I didn't say, there are actually two separate tubes. For one tube goes this way and the other tube goes the other way. Those tubes only intersect at where the detectors are. Otherwise, they're actually separate vacuum tubes in each direction.
What's the reason for using the superconducting magnets? Potentially the magnetic field.
So the question was, why do we use these superconducting magnets? The magnetic field inside is, I believe it's 12 Tesla. That's a huge magnetic field. The magnetic field, for instance, from the Earth's atmosphere is about half a Gauss. So a Tesla is 10,000 Gauss. So it's orders of magnitude stronger than the Earth's magnetic field. And some of the strongest magnets that have ever been built are about 100 Tesla or something like that. In order to get to those fields, you have to have a huge amount of current running through the magnets. And the only way you can keep the currents going without having immense amounts of power is to make them superconducting, to reduce the resistance. So that's basically why.
I have two questions, and they're probably both a little silly. If you've got two tubes, one going in each direction, and you've got the collider chamber, or whatever you call it, and they come in from the opposite directions, how do you make sure that once they go into this chamber, they continue, that the guys coming from this way don't go up the wrong tube?
Oh, that's a very good question. So the question is, you have these two tubes that intersect And how do you make sure they go, each one's going in the right tube? They actually intersect not completely head-on, but at a slight angle. And so when they intersect, they more or less hit an angle. One of them's already heading in that direction, the other one's heading in this direction. So they're actually heading down the two separate tubes separately. And then, I'm sorry, you had a second question.
And the other question was regarding a slide you showed earlier in the presentation about something being, I think it's like 100 times or 1,000 times hotter than the sun.
Right.
How do they contain that heat?
What I
didn't
the question, no, that was a great question. So one of the things I said was that if you were to take the energy of these two protons hitting, that would be equivalent to a temperature of about 100,000 times the heat of the temperature of the sun. Well, there's not exactly a lie, but there's a difference between temperature and heat. But that just means that these two particles have enough energy that if you were to convert that energy into a temperature, that would give a very, very high temperature. But heat is really kind of a cumulative thing of lots of them. And you don't have enough protons to make up a sun. So you just have very few protons, relatively speaking, hitting each other. So only at the interaction point. Another way of saying it, the total energy of each particle is very, very high, but the total energy is equivalent to the energy of, say, for instance, mosquitoes flying. I mean, it's very little total real energy in terms of, and that's what you would think of as heat. So there's not a lot of heat. It's just, if you were to take that energy and convert it to a temperature, that's what we want to do.
What's the probability of we're excited, accelerate lots of protons? What percentage of protons?
I'm sorry, I missed the last one.
Accelerate bursts of protons. Protons are very big in that lot of space. What percentage of collisions
Oh, you mean what percentage of the times you... Yeah, the probability of collision is actually very, very low. We measured it in cross-section. I don't remember the number offhand. And I forget the real numbers. But effectively, that every time there's a crossing of these two beams, there's kind of a probability of a few of those protons. And there are, I don't remember the exact numbers, but billions of protons, say, for instance, that are in each bunch, or whatever it is. And only a few of them will interact. So there's very low probability of, even with those bunches, of one interaction. But what happens is, because we have so many bunches crossing all at once, you can have, at any given time, when you trigger, you're going to have, on average, a few events actually occurring at the same time. And one of the hard parts is actually figuring out if there are more than one interaction at the same time, what they all get from. But the interaction probability is actually very low, and that's why you have so many bunches and so many particles. So yeah, you get it.
What else can you pump through the tube besides protons?
The question is, what else can you put through the collider? It's actually a very interesting thing, and it's a great question, because for what we're doing, we want to have very, very fundamental interactions, and so we just have these protons hitting. But you can actually look at collisions of all kinds of different things. So they'll be putting things like gold atoms and lead atoms and other heavier atoms colliding together. And that gives you a lot of information about the structure of nuclear material. So that's actually something that's been very interesting. It's actually not the field that I'm interested in, but so nuclear physicists are often interested in those types of interactions. And there's an experiment, not our experiment, but another experiment, which is meant to actually look at those types of interactions.
So there are other detectors?
Right, so I didn't quite show it, but this is just one of the detectors. There are basically four main detectors. Two of them, one of them called the Atlas detectors, the one I described. The other one is called the CMS detectors, very similar to the one I had shown. And there are two other detectors. One of them, called the Alice detector, is meant for exactly that, for looking at collisions of heavier nuclei.
After they're done analyzing all the data for the year, how are they going to apply that to space as a whole?
So the question is, how would you, after you look at all the data, how would you apply it to space as a whole? The point about it is that what people have some very interesting theories of what the world looks like as you get. One of the questions you might have, maybe it's not rattling around in your head right now, but one of the questions you could have is, what really happened if there was a Big Bang? What did it look like at the very, very beginning? And a lot of those particles that were produced have never been seen again, because you need these very, very high energies to produce them. after they're produced, because they're so heavy, they almost decay right away to other particles, and you never see those very, very fundamental, prehistoric particles. So this thing actually should be able to produce some of those particles, and from that we would actually be able to validate basically what the world looked like a very, very long time ago. Yeah.
Are physicists currently envisioning the need for an even larger accelerator?
It's always one of those things, everybody's always looking at the next thing. What's actually interesting is that our group here at the University of Arizona is already building prototypes for the upgrade of this machine. So one of the things that they want to do is not necessarily upgrade it to higher energies, but higher rates, to get more and more interactions, to even get a better view of what's, to produce more of these kinds of particles. So we're working on that. There's also an effort to build what's called a linear collider, where you'd have a very, very long device, and you'd have particles coming from both ends. And there's some advantages to having something which is straight rather than curved. And so that's kind of the next thing. Now, people have been talking about that for 20 years, and it's still not really on the horizon. So who knows when that would happen? But everybody talks about the next big thing. At night when you're falling asleep, you can always dream about something interesting. Yeah.
Just as a scale, there's a big trench, leftover trench over Waxahachie, Texas. If you scale up, there's a big trench there already.
Yeah, so that was you were saying in Waxahachie, Texas, right outside of Dallas, there's the beginnings of what was the SSC. They actually dug, I believe, a quarter of the tunnel. So the thing was going to be about 53 miles in circumference. So something about 2.5 times bigger than this thing in terms of scale. They canceled it after they saw cost overruns and all this other stuff. But they actually built that tunnel, and I don't actually know what there was some crazy talk about building a mushroom farm and all kinds of other stuff. But I believe the tunnel's still there, though I'm not sure. They may have filled in parts of it.
So how was all this paid for?
So the question was, how was it paid for? It's actually paid for, this is at a place called CERN. CERN is a multinational laboratory. So and the U.S. is not a member state, but a contributing state or something like that. That is paid for our contribution from the U.S. is paid for the Department of Energy. So the Department of Energy finances all kinds of things. One of them is basic research. The Department of Energy, just to give you an idea, morphed from what used to be the Atomic Energy Commission and all those things. So that unit was the one that financed all the nuclear energy and atomic bomb development that started in World War II, and it's morphed into what we have now. So the particle physics contribution of the whole Department of Energy is actually a very, very small fraction, but that's how a lot of this is funded from us. But I don't remember how many states there are, something on the order of 20 countries that are member states of CERN, and they all have some contribution that they make to this. Give you an idea, just the cost of this. Somebody asked me one time, I had no idea, but the cost of it total is about $10 billion. So you can say that either that's a lot of money or it's going to drop in the bucket relative to the price. It is a lot of money. Yeah.
Why is there only one colliding chamber in there, and why did they make it in a circle instead of in a straight line?
So the question was, why is there only one collision? There actually are 4 different sections where there are collisions happening. And that, why you have 4 versus 10 is really a function of civil construction. How many of these places can you build on the ground that you can afford, and also how many experiments can you think of that you would want to put down there. And so there are actually, I think, a few more than 4, but 4 is really the big number of big chambers. Why would you make it in a circle? Well, the reason you make it in a circle is because it's, well, first of all, to get to the energy that they want, or let me turn around. The first thing you want to do is you want to have lots of collisions. So you want to have these particles go around and around and around as many times as you want. And so that gives rise to the circle. But in order to make sure that you don't lose too much energy, you have to make the circle really big. Something that's straight, the amount of energy loss is much smaller than if it goes in a circle. So that's why you would build something straight. But then in order to get the energy that you want, you would have to make it much bigger, much longer. Well, that's it. I'd like to thank you for your attention, and thank you for inviting me.